Okay, here we brought forward the information we obtained for problem 8. Now we're looking at problem 9, and I probably ought to throw that up in the corner. Okay, now this is the information from problem 8, and you should be real familiar with that from the preceding video. So that in problem 9 you have delta S of 1.6 meters down the incline. That's the information that the cart coasts 1.6 meters down the incline. Okay, gotta remember to put my hand down here because the camera's a little higher than my hand. Okay, now delta S is negative 1.6 meters times I then, because down the incline is the negative I direction. If you recall the picture from the preceding video, and if not, go back and take a quick look at it. It's right there at the beginning. Okay. So delta S is negative 1.6 meters times I, and we ask the work by what's the work by W parallel? Well, it's W parallel dotted with delta S, which is, let's see if I left the I off of anything else. Okay, which is negative 0.025 newtons times I dotted with negative 1.6 meters times J times I. Not sure where that J came from. There's not one on the board, so obviously misfire of neurons in somebody's head. Okay, now we take this dot product. Well, what's a dot product? It's easily calculated by I component multiplied by I component. So that equals, well, what's 1.6 times 0.025? I believe that's 0.04. Yeah. That'd be 0.04 Newton meters equals 0.04 joules. And I'm trying to make a J out of the joules. I don't know, I got J in the brain. Okay, now that's a big ugly J, stands for joules, because Newton meters equals joules. Notice that there's no I or J on this. I dot I is 1. Okay, J dot J would be 1. I dot J is 0. Remember the definitions that lead to the definition of the dot product. Okay, so anyhow, so in this case, gravity, or the parallel component of the weight, does positive work. Now, if you recall, the incline is like this. The weight vector is straight down, so that the projection of the weight vector onto the x-axis is negative. Okay? That's why the negative 0.025 newtons times I. The displacement down 1.6 meters times I. The force and the displacement are in the same direction, both in the negative direction in this case, which gives you positive work. The parallel component of the force does positive work, positive 0.04 joules of work on the car. Now, what's that going to do? Well, that's going to tend to increase the speed of the car, but there's also friction involved, and if the friction was greater in magnitude than the parallel component of the weight and in the opposite direction, which is the case here, the opposite direction, not the greater magnitude, the car would actually slow down despite the efforts of the parallel component of the weight to speed it up. Okay, well, let's calculate now what the work by friction. Work by friction. Now, intuitively, we know displacement's this way, force of friction is this way. So the two are in opposite directions. The friction is going to do negative work, so we just multiply 0.01 newtons by 1.6 meters and put a negative sign on it, and we've got the answer. But I want to formalize this, and one reason I want to formalize this is to emphasize the fact that, number one, you do need the physical intuition, and you need the pictures to be sure you see what's going on. having been sure that you've set everything up correctly in terms of what you see, in terms of your pictures, in terms of what you intuitively understand, you then go to the formal calculation to make sure your spacecraft doesn't crash into Mars. Okay, that was this kind of error that caused that one, but a couple $1 billion down the tubes, and that was in 1990 something dollars. Yeah, it's the kind of mistake you don't want to make, and you probably want to reconcile this with the pictures, with what you get with the triangles, with what you get in many different ways to be sure you're right. And I'll say this is a difference, and you all are going to be in better position than I am to make a decision on this. It's the difference between getting the answer quickly and getting the answer right. Okay? And to do that, you balance what it's going to cost to do it right against what it's going to cost to do it quickly and against your budget. But I think we're moving more and more toward projects where engineers' time is not the huge factor in the budget, and you need to be able to get it right. Of course, when you're in an engineering situation, you make that decision. Your boss makes that decision. Your supervisor, your company, somebody makes that decision, whether you work quickly or work correctly, whether you have more emphasis on getting it done fast or getting it done right. Okay, anyhow, end of digression. Work done by friction. Well, friction is going to exert a force in the direction opposite motion, so that the force of friction, the vector force, is going to be plus 0.01 newtons times I. And plus because this is the positive x direction. The parallel component, not the parallel component, the delta S is the same as before. It's negative 1.6 meters times I. So that F friction delta S is 0.01 newtons dot delta S times I dot negative 1.6 meters times I want to write J by contrast. And of course that's not what you do. If we're writing a vector in components, we do the I component, then we do the J component, and I kind of tend to follow in that habit, and I've got to watch myself. Everybody's got to watch themselves. Okay, me more than others maybe. Okay, 0.01 newtons times I dotted with negative 1.6 meters times I dot I is 1, and then we multiply the 0.01 newtons by the negative 1.6 meters, and we get negative 0.016 joules. Prettier J than I had there. Okay. What else do we want to calculate? Well, we might want to calculate the work done by the net force. And I haven't really written. I'm going to call this delta W. Parallel by the, for the weight component, parallel is a capital W as opposed to lowercase w. This is delta W friction, not a vector, work as a scalar quantity. And now we're going to do delta W net equals what? Well, the net force is negative 0.015 newtons times I, just obtained by adding the parallel component of the weight to the frictional force, that's a vector. Okay, so we get delta W net equals what? It's going to be F net dot delta S. That's going to equal negative 0.015 newtons times I, newtons times I. Kind of bunched up there, hopefully you can read it. And not equals, but plus the displacement vector, which is negative 1.6 meters times I. And when we multiply that out, we get positive 0.009 joules. So that's delta W net Okay? And something's wrong here. This and this should add up to this, and they don't. What did I do wrong here? If I can find it quickly, I'll fix it right away. If I can't, things are looking bad right now. Okay, I'm going to pause the video for a second. I'll come back in a second. Okay, now as you probably picked up, I made a couple of mistakes here just to illustrate my point about being very careful in reconciling things. Believe that? Okay. Mistake here was I didn't have enough zeros on this one. The mistake here is that 1.5 times 6 is 9, but 1.5 times 1.6 is 2.4. That should have been 0.024 joules, so that now if I add this and this, I've got 0.04 minus 0.0016, which gives me the 0.024 joules. So that the work done by the parallel force plus the work done by friction does equal the work done by the net force.